better than in Delhi, where it seems to be a foggy and a smoggy day. And the sun is not yet out, but hopefully you people are having better weather. So we continue with our discourse on vectors. As we know, this is a course on statics, but these are the preliminaries. So today I will continue with vectors. Last class we defined vectors. We talked of addition and subtraction of vectors, multiplication of vectors, addition of vectors, etc. Now, the first thing we see today is the concept of a unit vector. A unit vector is a vector in a given direction with a magnitude equal to 1. That means the magnitude of a unit vector is always constant, and this is 1. We denote a unit vector in a general terms by letter E put with a hat. Normally hat is reserved for a unit vector, and there could be a subscript A or B or AB, etc., which identifies the direction of the unit vector. And so if we have a vector A, then unit vector in the direction of A physically, this is a vector A. Depending on the quantity it represents, it could have its units. For example, if I am talking of a force, this could be a force of 800 newtons. Now, if I want to find a unit vector in the direction of A, so what I have to do is I have to move along this direction, and the length which I move has to represent a magnitude of 1. So therefore, if I write this unit vector as E sub A, this will be equal to the vector A divided by the magnitude of vector A. And this is how we find a unit vector. If I know a direction, if I have to find a unit vector along that direction, this is what I would do. What I am discussing here right now in the initial part of today's class will be some general concepts involving vectors, and then we will look at all these concepts with respect to rectangular coordinates, and there we will talk of specific unit vectors, about some of which you may be aware, I, J and K, and they are also unit vectors, but they are unit vectors along some specific directions which we will discuss slightly later. So having discussed the concept of a unit vector, let me now introduce dot product of two vectors. Yesterday in the vector operations, we looked at addition of vectors, we looked at subtraction of vectors, but we did not talk of a multiplication of vectors. Now, it turns out that vectors can be multiplied in many ways. And one of the types of multiplication of a vector which we have, which is a very special type, which is called a dot product, and there is another name of this which is also called the scalar product. So if we have a vector A and a vector B, then the dot product of these two vectors is given by, so dot product, first of all, when I talk of a dot product of A and B, then this quantity is a scalar. It is not a vector, and it is not a higher order quantity which, like somebody asked in a question yesterday, called a tensor. This quantity is a scalar, and this is given by So let us say if C is equal to A dot B, that is how we write, and this will be equal to magnitude of A times magnitude of B times cosine theta. And let's introduce what is theta. Theta is the smaller of the angle between vectors A and B. When we have two straight lines, then the angle between them could be either a small angle or a big angle, and we choose the smaller of the two angles. And let us illustrate this. If this is vector A and this is vector B, then we join the two tails together, we just extend it, and the angle between these two, this is the smaller angle. The larger angle would be the reflex angle between A and B, which would be 360 minus theta. So this is how we denote this. Suppose, let me take another example. We have a vector A going like this and a vector B going like this. So once again, we will extend the back ends of the two vectors till they intersect. Now between A and B, either I could choose this angle or I could choose this angle. And which one will I choose? I will choose the smaller of the angles, and so this angle is what is theta. And from these two examples, and if you do these general things, what you will realize is that theta has to lie between 0 degrees and 180 degrees, both being inclusive. So it could be from 0 to 180, or if I put it in terms of radians, then I will put it as between 0 and pi radians. So this is the definition of this is how we define dot product. In a dot product, so what we have seen is A dot B. This is a scalar quantity, magnitude of A, magnitude of B, cosine theta. So now if A dot B is 0, what does this mean? This could mean three things. It could be either the vector A is 0. If it is 0, its magnitude will also be 0. Or it could mean that the vector B is 0. But then there's a third case. Even when A and B are not individually 0, A dot B could be 0 if cos theta is equal to 0, and this would mean that vector A is perpendicular to vector B. So that means if these two vectors are mutually perpendicular, then A dot B will be 0. Now what happens if A is parallel to B? There could be two such cases. One is A and B are parallel and they are along the same direction. Or we could have vector A like this, vector B like this. Maybe some people may call it anti-parallel. In this case, what will happen is the magnitude A dot B in this first case will be equal to magnitude of A times magnitude of B. In this case, when both of them are parallel, and here actually, if you see, theta is equal to 0 degrees. But in the second case, when A and B are anti-parallel, then you will see that theta is equal to 180 degrees or pi radians, and A dot B will be equal to magnitude of A, magnitude of B multiplied by -1. That means a dot product, while it is a scalar, it could have a sign. It is an algebraic quantity. It could be positive or it could be negative. Now, let me show one more thing. Suppose if we have a case of three vectors such that A dot B is equal to C dot B. If this is given to me, what does this mean? So this I can write it as vector A minus vector C dotted with B is equal to 0. And therefore, using my earlier conclusions, what we could get is that either case 1 A is equal to C, case 2 vector B is 0, or case 3 that A minus C is perpendicular to B. That means if A dot B is equal to C dot B, it doesn't mean in general that vector A has to be equal to vector C. This condition, vector A is equal to vector C, is only one of the three conditions. But if I have A dot B is equal to C dot B for all B. Now you see I have changed the statement. The earlier statement was A dot B is equal to C dot B. Now I am saying A dot B is equal to C dot B for all B. This would imply vector A is equal to vector C, because now you are eliminating the second and the third conditions here, because you are saying this is valid for all B. All B means B may or may not be 0. All B also means A minus C may or may not be perpendicular to B. And that is why in this general case, vector A would be equal to vector C. Now, we also realize one thing, that this dot product is commutative. What's the meaning of commutative? That A dot B is equal to B dot A. Now, to you it may look, well, this is a multiplication, so this is always commutative. Well, as we will show in the next example or next type of product, this may not be always commutative. Now, one thing you may be wondering, I'm going on and on with these topics of vectors, and this is a course on statics or on mechanics. Where does this quantity dot product appear in our mechanics? And the dot product will come when we talk of, let us say, the quantity called work done. And work done is defined as dot product of force and the displacement caused by this force. And that is what we call as the work done by the force. So if we take a dot product of these two quantities, that is what gives us the work done. And so this quantity, the dot product we are discussing now, is an important quantity in mechanics. Next, I will talk about another type of product called the cross product. And there's another name to this. It's also called the vector product. Now, in mechanics, where does cross product come into picture? It comes into picture when we talk of moment of a force. Moment, in fact, of any quantity is essentially a cross product. So we will, just as we have moment of a force, there is also moment of momentum, which is also called angular momentum. And this quantity is also a cross product. So now, what is the meaning? What is a cross product? So again, if we have two vectors A and B, then if we define the cross product of A cross B as C, just ignore this. If A cross B is given as C, then C, the cross product, this is again a vector. So notice, as opposed to the dot product, the cross product is a vector, and this is given by magnitude of A times magnitude of B times sine theta. So these are all scalar quantities, and its direction is given by a unit vector n. So again, because I have put a hat, this means a unit vector n. And let us explain what is the direction of n. So firstly, the cross product is in a direction which is perpendicular to the plane containing the vectors A and B. So for example, if this is vector A, this is vector B, then A cross B. So right now they are in the plane of this paper which I was writing. The vector A cross B will be perpendicular to this plane. Now perpendicular to this plane, you will realize there can be two directions. A direction coming out of the paper or another direction going inside the paper. How do we decide which is the direction of n, coming in or coming out? And this direction is decided by what we call the right-handed rule. How do we get to the right-handed rule? We look at the vector A and using a right hand. So if you are using a pen, please drop your pen if you are a right-handed person. You look at take the right hand and you move your fingers of the right hand from A to B. You curl the fingers in the direction from A to B. And the direction of the thumb, if I'm going from A to B like this, you see the curve, the direction of the thumb, which is now coming out of the paper, that gives me the direction of n. So curl fingers of right hand from A towards B using the smaller angle. Of course, this has in the direction of theta, not 360 minus theta. So we move from A to B, and the direction of thumb gives direction of n. So this is the rule, and in this case we will show n like this. We show it with a circle containing a dot. Circle containing a dot means this circle represents an arrow. Now when we have an arrow coming out, you will see it as a dot. So this represents a vector coming out of the paper. Now let me just show the opposite of this. Suppose if this is the vector A, this is vector B. Now how do we get the direction of n? So to get to the direction of n, firstly we work out, this is the angle theta. So now I take my right hand, fingers of the right hand, I move from A to B. When I rotate my fingers from A to B, what happens to my thumb? My thumb is pointing inside the paper. So therefore the n direction here points inside the paper. So how do I represent that? That is shown as a circle with a cross. That means if the arrow is going inside the paper, what will you see on the paper? The tail of the arrow. So this X represents the tail of an arrow. So that means n we will show either like this or like this, and the first case shows n pointing out, and the second case shows n pointing in paper. So this is how we represent the cross product. So once again I'll write this. We showed that vector C, which is equal to A cross B, this was equal to magnitude of A, magnitude of B, sine theta. So now one thing you will realize, if vector A is parallel to vector B, what does this mean? If vector A is parallel to vector B, that means either theta is equal to 0 or theta is equal to 180 degrees, and then A cross B will be equal to 0. And if vector A is perpendicular to vector B, this will imply A cross B, the magnitude of this will be equal to magnitude of A times magnitude of B, and it would have, if these vectors are perpendicular, the direction of course will be either n coming out or n going in as per the directions of A and B. So now once again, if we see, let's do the same things which we did for the cross product. I'll do them for the dot product. I'll do them fast. But now what we realize is the properties of a cross product is that cross product of two vectors, firstly it is a vector and its line of action is perpendicular to plane containing vector A and vector B. Secondly, if you look at the magnitude of A cross B, as we said, this is equal to magnitude of A, magnitude of B, sine theta. You will also realize that if this is vector A, if this is vector B, then the magnitude of A and A cross B, this is nothing but the parallelogram. Then area of this parallelogram gives me the magnitude of A cross B. Okay. Now, if A cross B is 0, then again we'll have three things. Either A is equal to 0, or B is equal to 0, or A is parallel to B. It is one of these three things. Okay. But if we have, again as before, if I have three vectors, I have A cross B is equal to C cross B. If only this statement is given to me, then I can write this as A minus C cross B is equal to 0, and then going from the earlier statements, it is either vector A is equal to vector C, or vector B is equal to 0, or A minus C is parallel to B. But once again, if it is given to me that A cross B is equal to C cross B for all B, and sometimes the mathematical symbol used for this is a V with a cross. This means for all B. Then this will imply vector A is equal to vector C, because I have these three conditions. Since this is valid for all B, the last two things are special cases. It's valid for all B, so vector A has to be equal to vector C. So this is the cross product. Now, using this cross product, I'll define something which we call as, firstly let me define an orthogonal triad of vectors. If I have three mutually perpendicular vectors, A1, A2, A3. If they are mutually perpendicular, we also use another word for these. We call them, they are orthogonal. Now if I take 3 unit vectors along A1, A2, A3. Let me call these unit vectors as E1, E2 and E3, where E1 is along A1, E2 is along A2 and E3 is along A3. Now what we say is, if the unit vectors follow the right-handed rule. What do we mean by right-handed rule? That if we put them in order, we have 3 unit vectors now, E1, E2, E3. Now, if I take E1 cross E2, now the cross product of E1 cross E2 will be magnitude of E1 times magnitude of E2 times sine of the angle between these two. Now, this has to be 1 because magnitude of E1 is 1, it's a unit vector. Magnitude of E2 is 1, it is a unit vector, and theta, because they are mutually perpendicular, is 90 degrees. So this has to be 1, but now, and also its direction. So this is the magnitude, and its direction can be either along E3 or minus E3. That this is the only possible direction because E1, E2 and E3 are mutually perpendicular to each other. So the direction of E1 cross E2 will be either along E3 or along minus E3. Now when I say it follows the right-handed rule, what is the obvious meaning of this? That E1, E2 and E3, they form a right-handed combination, which means if E1 cross E2 is equal to E3. This is what we mean by saying that they follow a right-handed system or right-handed rule. So let's say, for example, this is a unit vector E1, this is the unit vector E2. Which direction will be E3? Coming out of the paper or going inside? If E1, E2 and E3 are forming a right-handed system, then the direction of E3 will be coming out of the board, and this is what forms a right-handed, and we use a special word for this. We call it a right-handed triad. And if we are talking of 3 unit vectors which form a right-handed triad, this is called a right-handed triad of orthogonal vectors, or in fact if they are unit vectors, then we will use the word, we use one word, orthonormal vectors. So this is just a terminology. Now what's the meaning of a right-handed triad? As we have shown, E1 cross E2 will be equal to E3. This is just the first thing. So if I put them in a clockwise order, I have 1, 2, 3. And what you will realize is in this case, 1 cross 2 is equal to 3. So similarly, when I go from 2 to 3, if I follow the arrow, E2 cross E3, you can check this out. This will give you E1, and E3 cross E1 will give you E2. And if you follow otherwise, if you look at E2 cross E1, this will give you minus E3. So let me write it again. Let me put it very clearly. E1 cross E2 gives me E3. But if I reverse the order, that means I look at E2 cross E1, this will be minus E3. And similarly for the other ones, E2 cross E3 gives me E1, and E3 cross E2 will give me minus E1. And similarly, I will go to the third one. E3 cross E1 is equal to E2. And if we inverse this, E1 cross E3, this will be minus of E2. And all obviously, because all these vectors are mutually perpendicular, if I look at E1 cross E1, this will be 0. E2 cross E2, this will also be 0. And E3 cross E3 is also 0. So this is the full expansion of uh, orthogonal triad. Now we also see some more properties here. If I look at a dot product of E1 dotted with E2, because these are mutually perpendicular, this will be 0. Similarly, E1 dotted with E3 will be 0, and E2 dotted with E3 will be 0. I look at the dot products of the vector with itself. E1 dotted with E1 is always 1. E2 dotted with E2 is also 1. And E3 dotted with E3 will also be always 1. So these are some properties of unit vectors and what we called as a right-handed triad of orthonormal vectors. One more thing you must have realized from this discussion, what I told about the commutative property for a dot product, that is not valid for a cross product. You can clearly see E1 cross E2 is equal to minus of E2 cross E1. So therefore the cross product does not follow the commutative law. So now, having seen this, let us see how these facts will be used, and what we will emphasize in the course is using all these quantities which we have, forces and all, to use vector notation for that, and the convenient way of representing these vectors is using a Cartesian system of coordinates. How do we make a Cartesian system of coordinates? First of all, we fix a point O in the reference frame from where we are measuring the quantities. The quantity could be distance, it could be force, it could be anything. Somewhere we fix a point O. And now here we choose three mutually perpendicular directions which follow, choose three mutually perpendicular directions and excuse me, is it on or? Okay, sorry, I couldn't see the picture, so I thought I had gone off screen. So we have three mutually perpendicular directions and which follow a right-handed rule. We have already seen E1, E2, E3, which we had talked earlier. So the first of these directions we call as X. The second direction we call as Y. And the third direction, now the third direction has to follow the right-handed rule. That is very important. It cannot, so therefore if X and Y are like this is how we show X, Y in most problems, then Z direction has to come out of the paper. It cannot go inside because we want the right-handed rule to follow. So these are the three directions X, Y, Z. Now in this reference frame, these directions are fixed. So now a unit vector along X direction, how would we call it? Going by our notation, we would call it Ex. So that means it's a vector of magnitude 1 along this direction. But as is our notation, instead of calling it Ex, we more popularly call it as I. So a unit vector along the X direction is termed as I. A unit vector along Y direction is termed as J. And a unit vector along Z direction is termed as K. So we have these three unit vectors Ex, Ey, Ez. So we have now in this XYZ coordinate system, we have three unit vectors I, J, K, and I could even call this as E1, E2, E3. If I am doing this, and the E1 represents the X direction, E2 represents the Y direction, and E3 represents the Z direction. And then because this is a right-handed system, all the dot and cross products which we wrote for E1, E2, E3 are now valid for ijk. And just to illustrate the point further, for example, I cross j would be equal to k and j cross k would be equal to I, and so on. Now, let me look at some special things in, first let's look at 2D formulation. That means we are talking of only two directions, x and y. We are in two-dimensional plane. And let us say there is a force F. Now, let this force F make an angle theta. So, force F, which makes an angle theta with the x direction. Now, I have shown x and y as horizontal or vertical, but x or y could also be chosen as perpendicular directions. It could be along the incline, it could be perpendicular to the incline. So, we can choose x or y in any possible way. So, y direction, it need not be always horizontal and vertical. Now, let's talk of, so we have this is the x direction, this is the y direction, and I have a force F. Now, I talk of x component of the force, and this I will write it as scalar fx times I, and this will be given by, if this angle is theta, this will be given by magnitude of f times cosine theta. And similarly, the y component of the force, which as a component is a vector, this is the y component of the force, this will be equal to, if I write it as Fij, then this will be equal to, in terms of x, in terms of the variables given, F sine theta j, and the force F actually is equal to Fx plus Fy, and this will be equal to F cos theta I plus F sine theta j. So this is what I call as solving the force F along its I and j components. Now, Fx, Fy by themselves, if I write them as scalars, they can be positive or negative depending on theta. If theta makes an angle between 0 and 90 degrees with positive x-axis, then Fx will be positive and Fy will be positive. And in fact, it will be strictly greater than 0 if this is not 0 or 90. Now, if theta makes an angle between 90 degrees and 180 degrees, then you will see Fx will be less than 0 and Fy will be greater than 0. And for the exact case when they are equal to 90 or 180, then the equality sign would come in here also along with the inequality sign. Okay. So what we have here is the magnitude of, so Fx component is written as F cos theta, F component is written as F sin theta, and if I know the components, then tangent theta is given by Fy upon Fx, and F, which is equal to the magnitude of the force F, this is given as square root of Fx square plus Fy square. Maybe to complete the picture, I will show this. This was the force F. This is the x direction. This is the y direction. We draw from F perpendicular to y. Wherever this hits, this is fx, this angle is theta. We draw from the tip a line parallel to the x-axis. Wherever this hits, this distance is what is the scalar f. So this particular picture tells us the relation between all these things. So either we need to know fx, fy, or I need to know f and theta. If I know any two of the four things, I can determine the other two. So these are this thing. I'll take up an example also, but before I take up the example, in case if I'm not able to take up the example, you can look at the example in the textbook in chapter 2. But then let us see how do we carry out the dot and cross product with rectangular components. So for example, I have a vector A. This is equal to AXI plus AYJ plus AZK. I will take the three components now, and we have a vector B. This is equal to BXI plus BYJ plus BZK. And you will see, once we express things in Cartesian components like this, then taking dot products and cross products becomes quite easy. How? If I look at dot B, so I have to look at take the vector A, AXI plus AYJ plus AZK, and I dot it with the second vector, which is BXI plus BYJ plus EZK. And how do I open up these brackets? You take the first term here, dot it with the first term, and to that you add the dot of the first with second, dot of the first with third, and so on. So totally there will be 9 terms which will be added. And when I take the first term, I get AX BX times I dotted with I, which gives me 1. So it becomes AX BX. Next I take AXI dotted with BYJ. Now I dotted with J is 0, so this directly becomes 0. Next I take AXI, I dot it with BZK. I dotted with K is 0, so this also becomes 0. Next I go to AYJ, dotted with BXI. Obviously it is J dot I, it is 0. So I get a second term which is AYBY, and when I open the third term, I will get a third term which is equal to AZBZ. So using Cartesian coordinates, I directly get the dot product of two vectors as the products of the x components added to the product of the y component added to the product of the z component. And this makes my life much simpler. Similarly, if I have to find A cross B, how do I go about doing this? So this I will write it as AXI plus AYJ plus AZK, and we take a cross product of this. So crossed it with BXI plus BYJ plus BZK. Now you will see when I take I cross I get 0. I take I cross J. So the first term which I get is AX BY I cross J, which gives me K. I cross K will give me minus J. So this becomes minus AX BZ J. Then I go to AYJ. So I will get J cross I is minus K. So I get minus AY BX K. J cross J is 0. Then I go to J cross K. So then I get the fourth term plus AY BZ J cross K gives me I. Then I go to the third term. K cross I gives me J. So I will have AZ BXJ. K cross J will be minus I. So I have minus AZ BYI. So I get these 6 terms like this. And so I can carry out the cross product. And you probably must be familiar with this. A cross B can also be expressed for Cartesian coordinates in terms of a determinant. We write the determinant value of ijk, vector A, which is AX, AY, AZ, so this is A, and BX, BY, BZ. So if I express this, open up this determinant, I will be able to get the vector A. Now, one last thing I'd like to do, and this is something important, something you may not have seen, and which will be used many times in mechanics. Suppose I have a vector which is directed along B. Let the coordinates of A be x1, y1. Let the coordinates of B be x2, y2. So now, how do I write the vector AB? We are right now assuming it's only a two-dimensional problem. So the vector AB can be written as x2 minus x1i plus y2 minus y1j. If any of these x1, y1, x2, y2 is negative, then that sign also has to be included. For example, if x1 is minus 3, x2 is 4. So this first term will become 4 minus minus 3. So totally it will become 7i. So this signs of x1, x2 have also to be accounted for. The minus sign is as it is. Now, what is if length L is the magnitude of AB? What is the length L? And this you know from coordinate geometry, this will be equal to x2 minus x1 square plus y2 minus y1 square. So the next thing we may like to do is we want to find out a unit vector along this length AB. What will be the unit vector along this length AB? This, as we have seen, this will be AB divided by the magnitude of AB. So this unit vector along AB will be equal to the vector AB, which is x2 minus x1i. I have to divide it by the length L plus y2 minus y1j, again divided by L. So this is how I get the unit vector along AB. And what we will realize is that if the vector, if AB makes an angle theta with the x-axis, this is the y-axis, then cosine of theta will be equal to x2 minus x1 by L, and sine of theta will be equal to y2 minus y1 by L. So now, suppose if we have a third vector C and we want to find component of C along AB. So we have a vector C, we have a vector AB. We want to find what is the component of C along AB. Now let the vector C be Cxi plus Cyj. So now component of C, and this is where now the Cartesian system comes in very handy, along AB. This will be equal to the vector C dotted with a unit vector along AB, and if we have to express this component as a vector, then the direction of this component is given by the direction AB, which is unit vector along AB. So now C is equal to Cxi plus Cyj. We have already worked out the components of EAB, so we just have to take a dot product. So now if I repeat these again, C was equal to Cxi plus Cyj, and a unit vector along AB, this we had written as x2 minus x1 upon Li plus y2 minus y1 upon Lj. Then C dotted with EAB, this is the magnitude of the component. This will be equal to Cx multiplied by x2 minus x1 upon L plus Cy multiplied by y2 minus y1 upon L. And if I put this whole scalar along with EAB, this will give me the vector component. Now, Yeah, but I'll just answer. But before that, now what is the component of C? And this is the main thing which I want you to learn. Component of C perpendicular to AB. This component will be equal to the total vector C. From there you subtract the component of C along AB. What is that? C dotted with EAB times EAB. So I will leave you with this thought that this is how you find the component of C perpendicular to AB. That from the total vector C, you subtract the that part of C which is along AB, which is the scalar component times the unit vector EAB, and the net thing which you get, this will be the component of C which is perpendicular to AB. We need these things in mechanics, particularly when we talk of normal forces and shear forces. So I'll stop here and I will now take questions. We have a couple of questions. Yeah, PCE is it coming now? No. Let's try the other one then. Is there anything else? So PCE, you have a question, please? Please ask. So are there any more questions? Because I stopped because I thought there were questions. If there are no questions, then maybe I will take up an example. I'll take
Hello,
one
can
more.
you hear
In
me,
this
sir?
case, so now,
Hello.
so let's take an
Hello.
example because PC is
Hello.
not asking. Okay. So let me take an example now. This is again an example from the text. We have, see now what I talked of. If you have a force along this direction AB, you know the coordinates of A. So XA, YA are coordinates of A, XB, YB are coordinates of B. Where do you actually use this information in mechanics? Let's try to get to that. Suppose if there is a rope which is pulling along AB. Now the force in the rope, this is normally, we use the sign T for this, we call it the tension. Now, what is the direction of the tension? The direction of the tension will be given by unit vector along AB. And so, this tension, if we have to express it as a vector, this would be equal to T times unit vector AB, where T is the scalar force. And this is how you would use this to for in problems to solve for writing a vector, writing a force as a vector when you know 2 points along which it operates. So, okay. So, as an example, let's say there's a post AB at the point B. There's a rope which is tied to the wall. This is a wall. The rope is tied to the wall at point C. And at the point B, there's probably some pin or something. There's a force of 500 newtons tied like this, and there's another force of 780 newtons, and of course we have this rope in which there's a tension which is given to be equal to 725 newtons. And the problem asks us to find the sum of all these forces, find sum of the forces acting on B. Sometimes for sum we also use the word resultant, find the resultant of these forces. Now here, as for dimension, and this is how we do, here for direction what is given is a triangle is drawn, this is shown as 3, 4. This means the direction of this is given as per a triangle of size 3 and 4. In this case, again a triangle is drawn here. This is shown as 12. This is shown as 5. And for the third case, this component is given as 800 mm and this length is given as 840 mm. So we have two forces who are specified in a way with the triangles and the third tension where the dimensions are given. So now let's call this force as F1. Let us call this force as F2. Let us call this force as F3. So to find the force, what we have to do is express each of F1, F2 and F3 in terms of I and J. So now if this angle is theta, so what we realize is F1 will be equal to T cos theta I plus T sin theta J, where I am, for the final answer, I am assuming X and Y like this. So now notice I have taken theta with the minus X axis, that is why I put it as just T cos theta, and along with this, if theta is the angle with the minus X axis, I should put a minus sign also. So please note this minus sign is important because the component of X is T cosine theta, but with a minus sign because it is along minus X axis. So, and here what is cos theta? If this length is this much, then this hypotenuse, this will be equal to 1160. So cos theta will be equal to 840 upon 1160. Sin theta, you work it out, simplify it, it turns out to be 20 upon 21. So this is how you will get F1. Look at F2. Now the X component, if this is 3, 4, the third side will be 5. So F2 will be equal to, if I call this as alpha, F2 I can write it as minus F2 cos alpha I minus F2 sin alpha J. And what I have is cos alpha, this angle is alpha, this angle, this was making the horizontal. So this angle again, this is a 3, 4 triangle. This angle will also be alpha. So cosine alpha will be equal to 3 divided by 5. Sin alpha is equal to 4 by 5. And similarly, you go to F3. Then you add all the I components, you add all the J components in an algebraic way, and you get your final answer as something I plus something J. Add up all the I components, add up all the J components. That is what will give you the final answer. You can look at the problem in the textbook. This is example 2 in chapter 2, and you'll be able to then work. Okay. Thank you very much.